My name is Emmanuel Taishan. I am a technical marketing engineer working for the IoT business unit. And today we're going to talk about some of the advanced concepts for IOx. You've seen a session on IOx earlier, and today we will focus on those specific aspects. And I selected those different subjects because this is the recurring subjects that I am seeing with the partners and the customers that I am working with. So we will talk initially about the fat container syndrome, which is commonly seen amongst container users. Then we will talk about the remote Docker workflow, which is an enhancement we have made to Cisco IOx specifically for developers and to support our developers community. We'll then run a demo, which is how to run Grafana, which is a graphical UI, so to speak, so you can make graphics and pie charts and line charts and everything. It has a web UI and all that. So we'll make Grafana run on a Cisco IR 1101 router using the remote developer workflow. So that is without writing a single line of code and by running Grafana directly from Docker Hub. And lastly, we will talk a little bit about the multiple CPU architecture and why this is maybe a source of concern, not that a big source of concern, but that's something you need to be aware of and something you need to work on if you want to have IOx applications running on a range of platforms. Based on my experience with many partners and many customers, I see very often what I call the fat container syndrome, which means people tend to confuse containers and VMs. But containers are not VMs. VMs are full-fledged operating system with services, and a single VM can actually have multiple services, a database, a web server, a backend. Containers not working this way. Containers are supposed to do one single, very specific task and should be lightweight. Okay, so don't confuse VMs and don't consider containers are lightweight VMs. That would be a mistake. Containers are designed to be light and designed to do very limited functions. That's particularly true when you run containers at the network edge where routers are and gateways are typically not super powerful. We're not talking about servers or Cisco UCS or anything like that. We're talking about embedded systems. Another reason for embedded systems, in particular Cisco platforms, is that fat containers has many issues. So don't do that because we have limited storage at the network edge. Some of those platforms, such as the IW6300 access point, has only 256 meg of storage space. Considering you need 3 times the storage space when you deploy a container because of temporary file writing requirements, overlay FS, etc., etc., you need to be very careful about your container size. That's a problem we see very often. The speed, some of those platforms use the MMC flash, which is not super fast. It's made to load Cisco IOS images. It's made to be primarily used as a read-only. So, a big image might take time to deploy. Processing time. We don't have a lot of CPU resources and storage might be slow if you run on the MMC. So big images takes time to deploy, takes time to process. So keep them small. Flash is wearing off. So every time you write, but if you are wearing out the flash. So if you write a 50 meg container, it's better than the 500 meg container because you limit the wear and tear on your flash drive. And lastly, very specific to the IoT world, but we have a lot of our platforms that are running in remote and mobile facilities, such as hard to reach location over cellular network. Cellular network are typically slow, in addition, expensive to run. So big images means a lot of money spent on cellular fees. So a couple of ways to do that. Tip number 1, always start with a light root FS. I see many people starting containers with Ubuntu because they're already familiar with Ubuntu as an operating system. But as you can see, Ubuntu weighs 188 megabytes for the base root FS. So without even doing anything, you have a big containers. As opposed to the complete opposite of the spectrum, which is BusyBox, Yocto Linux, and Alpine, which is 3 very good options for Docker. These ones weigh less than 5 meg. So I highly encourage to start with a minimum rootfs and add features as you want them. If you need Python, add Python. Ubuntu will start with everything from scratch, okay? We have made, as part of Cisco DevNet, we've made a number of rootfs Docker image available for you to build against most of our platforms. So those are Yocto-based, minimum rootfs that also include everything you need to run that on IOx. So please use that. Second thing is multi-stage builds. I've seen many times a need to compile a program, for example. In this case, it's a Go program in Golang. So to compile the program and then use that container. And I've seen many times that the compiler and everything remains in the final container. But once the container is running, you don't need that compiler anymore. You need the compiler just when you build it. So you can use something called multi-stage builds in Docker so that you can split your Docker file in multiple steps. The first step here is about starting from a Golang Docker image, compiling my hello world example. So I have a binary hello world. So I call that the build stage. And then my final, so that is not going to end up as in my final image. My final image start from here, from Alpine. So I take the entire Alpine 5 meg rootfs and I copy from the previous build called build stage, I copy my executable over to my current Alpine. And that's it. So I only have Alpine Linux with my hello world, no compiler, no libraries. So the result is you have very slim, very thin containers that contains meat and no fat. An example on how to do that is on GitHub, so you can check that example over here, where we started with the minimum rootfs for IR1101, which is ARM-based CPU. So we used the Yocto-based rootfs, compiled the hello world in C using GCC as a multi-stage build, and the net result is we have an IOx application that weighs only 4.4 meg, which is really not bad. Now that you understand what is remote developer workflow, we'll showcase how to run Grafana on a Cisco IR1101 using remote developer workflow. So this is the Cisco IOx local manager on the Cisco IR1101, but you will see the same interface on other platforms. Right, so let's start by logging in to the local manager. If your current platform and image support remote Docker workflow, you will see that option over here to enable it. So simply click on the Enable Remote Docker Access. Now that remote Docker access is enabled, the setup instructions are over here. So you essentially have to set up a few environment variables. You need to download the certificate. So the X509 certificate from the IR1101 to authenticate your Docker client to talk to the Docker engine on this particular gateway, as well as create here a JSON file with a base64 encoded value with a username and password that has access to the platform. All right, and very important, you also need to create a profile, which means the Docker application, the Docker container running on the platform will have to run under a specific context, which is the equivalent of application activation. So let's do that now and create a profile called Grafana. Oh, we can leave everything as a default, but we will add an Ethernet 0 interface to that container. As you can see, the interface settings is dynamic, which means it will get its IP address from the DHCP server running on the IR1101. So we add the interface and we confirm. All right, the profile has now been created. So every time you need to run an image or a container, when you type docker run, make sure you use those parameters. Those parameters will tell Docker to use this container as a network container, this use that volume, etc. So that's all the options that you need to pass on Docker to run with the remote developer workflow. We'll see how to do that in a second. All right, I'm now on the development machine. In this case, this is a Linux machine. The first thing we'll need to do is to pull Grafana from Docker Hub. So from the development machine, we can do a Docker pull. Well, in this case, we're going to use the Grafana ARM 64 v8 version because this is essentially what the IR 1101 is running. All right. So now that we have it in our local repository, we can save it. There we are. So we'll save it in a tar file that we call Grafana ARM64v8 linux.tar. So that will save that image to a tar file locally on my directory. So I now have Grafana here as a tar file on my machine. Now I need to set up the remote Docker workflow, which is essentially giving my remote Docker engine, which is in this case the IR1101 IP address. You know, I'm basically following the instructions that we've seen together in Local Manager a minute ago. All right. Then we need to download the certificate, right? So to do that, there we are, download the certificate. We'll place it in our home directory in a file called ca.pem. This is the default location. There we are. Then we need to base 64 encode our username password. So username password in this case is Cisco. I obviously do not recommend to use that in production, but we will encode it. So echo -n is to make sure we don't have a new line character. Okay, so this is our base 64 encoded username password. So now we will edit the docker config.json file. As you can see, we already did that, but you really have to replace here this string by the actual base 64 encoded value of your username password. That's for authorization. The TLS certificate is for authentication. All right, so let's check the Docker variables. So our environment variables are all set. Let's check if we're connected on the IR1101. So Docker info will give you information about your Docker client, but also your Docker engine. And as you can see here, I am connected directly on my IR1101. Okay. So what I'll do is I will now load the tar file that we saved on the first step, which includes Grafana. I will load it over to my IR1101. And there we are. Loaded, perfect. Let's check with Docker images and see what we have. So as you can see here, we have our Grafana image loaded over to the platform. That's perfect. Well, let's start the Docker image. Docker run. After Docker run, -D to run in daemon mode, so it will go in the background. Now we need to add all of the parameters we had in Local Manager previously, right? So that includes the network container, the volume instructions, the number of CPU shares, the memory usage, and at the last thing, the name of the image we want to start. So this image will essentially become a container when it's running. There we are. So one last thing, we said dynamic IP address when we set up the profile. So what's the IP address of that running container? Well, to do that, you can exec inside the profile. So the profile is called Grafana. In this case, the profile is called Grafana. So it's Grafana_PR sleep. You can check that with Docker PS, which is the name of your profile. And we simply execute inside that network container /bin/sh. So that essentially gives us a shell inside that container. And then we can check with ifconfig, right? And ETH0, remember that's the name we gave for our network interface, is 192.168.1.9. So remember that as we are now going to set up a NAT rule on the 1101 to make this work. So now that our container is running on the IR 1101, the problem is this container runs inside the private IP address space on the 1101. If we want to be able to access the Grafana Web UI, which runs on TCP port 3000, then we obviously need to configure NAT rules, NAT, Network Address Translation. So first of all, let's get into this platform, enter in configuration mode. And then do you remember the IP address was 192.168.1.9? So we will configure a NAT rule to source route, well, at least to map the static TCP port number 3000 on the IP address 192.168.1.9, which is our running container IP address, and we'll map that over the gigabit Ethernet interface 000, which is the primary router interface, port number 3000. To make sure it's working, let's go back to our browser here, where we have local manager, open a new tab, and enter Grafana IP address, which is the gateway IP address, port number 3000. And as you can see, it's working. So Grafana is now running on the IR 1101, and it's been pulled straight from Docker Hub. Cisco IOx platforms may be using different CPU architecture depending on which range of products you want to work on. So for the sake of simplicity, I will just talk a little bit about the enterprise products versus the IoT products. So enterprise products are typically installed in a data center or in a cabinet. They are typically rack mounted, directly connected to AC power. They have big fans blowing air through the chassis for cooling, etc., etc. So that's, like the IT space as we know it. I am working for the IoT business unit, so for us, we have different constraints. Typically, those platforms are installed in a closed cabinet because, for example, they have to work in an environment where there are explosive gases, and the platform cannot be directly exposed to gases. So we need to, shield the platform inside a completely sealed enclosure. Blowing air in a sealed enclosure is not helping. So for this kind of scenario, we need something extremely efficient, both in terms of power dissipation. So that's why we selected the ARM CPU. So for enterprise, they selected Intel CPU because it's widely available, but it's generate quite a bit of heat. But for us, we selected ARM CPU. So most of our platforms are using ARM. Actually, there is a few exceptions in there, namely the IC3000 and IR829 are still running on Intel. They're running on Intel Atom because it's very efficient from a power dissipation perspective. But all the other platforms and all the new platforms are going to run on ARM CPU. Because we install in cabinet, we don't have any ability actually to cool down with fans or with blowing air or anything like that. We typically have very limited DC power. So either because it's powered by solar panels or running directly off a battery. It could be a car battery, a boat battery, or anything like that. So for those different reasons, different branches are using different CPU architecture. But why does it matter? Because when you run IOx applications, IOx runs on Docker, and Docker is not an hypervisor. Docker does not abstract and does not abstract the platform CPU architecture, right? So if you build something for Intel x86, it's not going to work on ARM, and vice versa. The binaries are different, the extraction code is different. So my recommendation is, first of all, if you need to compile or if you need to use multiple CPU architectures, start with QEMU. You can install it on Linux, and QEMU makes it possible to run code on cross architecture, so you can run ARM code on an Intel CPU. So start with QEMU. Then second, there is a feature in Docker called BuildX, and BuildX makes it possible to build for a target architecture, which is not your build machine. So in this case, as you can see here on the right, we're going to build a single image for AMD 64, which is Intel, and ARM 64, which is ARM. And by using BuildX, you can specify the target platform you want to build for. And also, we are building it and tagging the resulting image with the appropriate architecture. right? And then at the end of the day, we are also packaging with IOx client our Docker image as an IOx app. So this kind of loop here will actually create images and IOx applications for two different architectures in one shot. So I have an example here. If you follow this, I have an example here on how you can do that on GitHub with all the details, including the build functions, the Docker file, and the package.yamls. So make sure you leverage Docker buildx to do that. Thank you very much. See you soon.